So we are now ready to officially start evaluating surface integrals. And we have two types of surface integrals that we're going to explore here. The first type is a scalar surface integral. And I want to begin by recalling how we evaluated scalar line integrals. So given a line integral over a curve C of a function f of x, y, integrating with respect to the arc length, to integrate this, we rewrite this line integral over the curve C as the parameterized function f of x of t, y of t, and we multiply this by the magnitude of the tangent vector with respect to t. So here, when we're looking at evaluating scalar line integrals, we have a one-parameter description. So with scalar surface integrals, we are transitioning to a two-parameter description. So here we go. And we're going to draw parallels to our good old friend, the scalar line integral. So here we go. To begin, we want to let f of x, y, z be a continuous function on a smooth surface S in space. And we want to think to ourselves, okay, well, what if this surface S is defined parametrically? So we know that we can then redefine this surface as the parametric representation vector r of uv with components x of uv, y of uv, and z of uv. So there's our two-parameter description. And this is where the ordered pair uv is in a region R, where R is in the plane. R is in R2. Alternatively, we could also write this as R is the set of all ordered pairs, uv. And let's actually incorporate bounds on these parameters. So let's say that u is greater than or equal to a, less than or equal to b, and v is greater than or equal to c, less than or equal to d. And this, of course, is where a, b, c, and d are all scalars, are all constant values. So now that we have our parametric description of the surface, we're then ready to define the surface integral. So we can say then the surface integral is a double integral over this surface S of the function f of x, y, z, and we're integrating here with respect to the surface area. So we need to parameterize this integral. So this becomes the double integral over that two-dimensional region R in the plane of the parameterized function. So this is f of x of uv, y of uv, z of uv, and we're going to multiply this by the magnitude of the tangent vectors. So keep in mind here, we have a two-parameter description. So the magnitude is of the cross product of the tangent vector in the u direction with the tangent vector in the v direction, dA. So this is our surface integral for a parameterized surface. And I want you to note here that this differential, this magnitude of the cross product of the tangent vectors in the u and v direction, is analogous to the tangent vector that we saw, the parameterized tangent vector that we saw back with scalar line integrals. So let's think about this in a little bit more detail. We can give ourselves more room here. So this is our surface integral over a parameterized surface. And so let's make a little love note here that this is where the vector t sub u is the tangent vector in the u direction. And so we define this as the derivative of our parameterization vector r with respect to u. So this has components the partial derivative of x with respect to u, the partial derivative of y with respect to u, the partial derivative of z with respect to u. We also have the tangent vector in the v direction. So this is defined as the partial derivative of the vector, or the parameterization vector r, with respect to v. And so this has components the partial derivative of x with respect to v, the partial derivative of y with respect to v, and the partial derivative of z with respect to v. And so using our knowledge of the cross product, we know that if these two vectors are tangent to our surface, they're parallel to the surface. And so we can define a normal vector here as the cross product of these two tangent vectors. And we want to note that this normal vector is non-zero. This cannot be equal to 0. So this is our definition for our surface integral, a scalar surface integral of a parametrically defined surface. And I want to go into a little bit more detail here, looking again at where exactly our differential here is coming from. So where is this surface area differential coming from? And so we are going to use our approximation of the surface area with Riemann's limiting process. So let's begin by thinking about, so again, we are exploring right now where the surface area differential comes from. So that's our ds. Where does this come from? And we can easily see where this is coming from by simply thinking about some arbitrary surface in space. So here we go. We can say here is our z-axis. Here is the x-axis. We'll move this up. And then last but not least, we'll think about our y-axis here. So we have z, x, and y. We're just thinking about the first octant in our surface. And let's draw ourselves a little surface here. So we have some surface in the plane, or in space, excuse me. So here is the surface we are considering in space. And we'll call this our surface S. And we want to find where does that surface area differential come from. So to see where this comes from, we want to think about a sufficiently small region here on our surface. And so let's go ahead and we'll take this little piece out. So when we think about this little piece, if we blow it up, make it a little bit larger, we realize, hey, we have a parallelogram. Right, so this little small piece is a parallelogram. And we have two important features of this parallelogram. You have a tangent vector here pointing in the u direction. So we can define this as the tangent vector in the u direction multiplied by some sufficiently small change in u. And then we have a tangent vector here pointing in the v direction. So that's a tangent vector pointing in the v direction multiplied by a sufficiently small change in v. And we have some angle here in between, some theta. And so we think to ourselves, how can we find the area of a parallelogram using two adjacent vectors, two tangent vectors? And you were right, we can use the cross product. So we can recall, we've already seen how to do this. So we know that the area of a parallelogram, is going to be equal to the magnitude of the cross product of two tangent vectors, or two adjacent vectors. So we can say, again, giving ourselves a little bit more room so we can still see that surface integral. We can say that, so again, we should be more careful here. We're still using an approximation, so we can say delta S. So the change in this surface area is going to be approximately equal to the area of a parallelogram, specifically this sufficiently small parallelogram that we have just taken off of our surface. And we know that we can define this as the magnitude of the adjacent vector. So that's going to be the magnitude of the tangent vector in the u direction multiplied by that sufficiently small change in u, And we'll cross this with the tangent vector in the v direction, multiplied by that sufficiently small change in v. And now note to yourself here that these two differentials, delta u and delta v, are scalars. They're constants. So we can actually pull those out of the magnitude. So that's delta s, the change in our surface area, is going to be approximately equal to the magnitude of the cross product of the tangent vector in the u direction crossed with the tangent vector in the v direction, multiplied by the change in u times the change in v. And so we can see here that this is approximately equal to the magnitude of the tangent vector in the u direction crossed with the tangent vector in the v direction. And this delta u times delta v makes up delta a. And so we can see here where this differential is coming from. Of course, this is an approximation. Right? We would need to get that full differential, as we have defined with the definition, we would need to use Riemann's limiting process. But at least we have a better understanding now of where this is coming from. And so now we need to think about the case where our surface is defined explicitly. So again, we're going to begin by letting our function f of x, y, z be a continuous function on a smooth surface S in 3 dimensions. But this time we want to think to ourselves, well, what if our surface S is defined explicitly? So if you're thinking, what do you mean explicitly? I mean that our surface will be defined as some z is equal to a function g of x, y. So z is defined in terms of x and y, and this is such that the ordered pair x, y is in that region R in the plane. So this is where R is still that region in R2, or in the plane. So we use this explicit notation to parameterize the surface S in terms of just x and y. So we have the parametric representation vector R in terms of x, y, and we define this as the vector with components x, y, g of x, y. So we replace that z with g of x, y. So using this, we can now go ahead and define the surface integral for a scalar surface integral for an explicitly defined surface. And this starts the same way that we did with the parametrically defined surfaces. We have that double integral over the surface S of the function f of x, y, z. And remember, we're integrating here with respect to the surface area. So we can now rewrite this as the equivalent double integral over that two-dimensional region R in the plane of the parameterized function. So this becomes f of x, y, g of x, y. And just like we did with the parametrically defined surfaces, we now multiply this function by the magnitude of the cross product of the tangent vectors, but this time we have a tangent vector in the x direction crossed with the tangent vector in the y direction, dA. So this is our surface integral, our scalar surface integral for an explicitly defined surface. And let's think about these components in a little bit more detail. So again, just like with parametrically defined surfaces, we have our two tangent vectors. You have the tangent vector in the x direction and the tangent vector in the y direction. So we know the tangent vector in the x direction is simply the derivative of vector r with respect to x. And to define these components, we want to think back to our parametric description of our surface. So we can say, taking the derivative with respect to x, we have the partial derivative of x with respect to x, you have the partial derivative of y with respect to x, and then you have the partial derivative of the function g with respect to x. And of course, we can simplify this. We know the partial derivative of x with respect to x is simply 1. The partial derivative of y with respect to x is simply 0. And then since we know at the beginning that our function g of x, y is defined as z, we can shorthand the z component as the partial derivative of z with respect to x. And we do the same thing for the tangent vector with respect to y. We have the derivative of the vector r with respect to y. And again, using our parametric representation here, we define the components. So we have the partial derivative of x with respect to y, the partial derivative of y with respect to y, and the partial derivative of function g with respect to xy. And we can simplify. So we have the partial derivative of x with respect to y goes to 0. The partial derivative of y with respect to y is 1. And we'll use our shorthand here for the partial derivative of g with respect to y and say that this is simply the partial derivative of z with respect to y. And using our knowledge of the cross product, we know if these two tangent vectors are tangent to the surface or parallel to the surface, then a normal vector is defined by the cross product of these two vectors. So we define the normal vector n as the cross product of the tangent vectors in the x and y direction. And using the components that we just found, we can go ahead now and define the components of our normal vector. So we can say that this is going to be equal to, we have 0 minus the partial derivative of z with respect to x times I hat, minus the partial derivative of z with respect to y minus 0 j hat, plus the partial, or plus 1 minus 0 k hat. And so this leaves us with the components of our normal vector minus the partial derivative of z with respect to x I hat, minus the partial derivative of z with respect to y j hat, plus k hat, or you can write this in its component form, minus the partial derivative of z with respect to x, minus the partial derivative of z with respect to y, 1. And so we'll use this normal vector here now to go ahead and compute its magnitude. So we can say that the magnitude of the cross product of the tangent vector in the x and y direction is going to be defined as the square root of minus the partial derivative of z with respect to x squared plus minus the partial derivative of z with respect to y squared plus 1 squared. And of course, we know anything negative that is raised to an even power, like we see within the radicand, is automatically going to be positive. So we can simply rewrite this as the square root of the partial derivative of z with respect to x squared, and we'll make that look a little bit more like a 2 instead of another z, so that's squared, plus the partial derivative of z with respect to y squared plus 1. All right, so we can now use this magnitude, the magnitude of the cross product of our two tangent vectors, and we'll plug it into the surface integral that we defined above to attain an alternative notation. So these, of course, are equivalent, as we have just seen, but this alternative notation can be helpful in computation. So this is the double integral over that explicitly defined surface S of the function f of x, y, z. And as always, we are integrating with respect to the surface area. And we can now rewrite this as the double integral over that region R in the plane of the parameterized function f of x, y, g of x, y, multiplied by the magnitude of the tangent vectors. So this is multiplied by the square root of the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared plus 1 dA. And so this is an equivalent alternative form that we will use when calculating a scalar surface integral of an explicitly defined surface. And one last little love note here before we go ahead and start looking at examples. I want you to think about the following. So I'm posing this question, what if we let the function f of x, y, z be equal to 1. So I want you to think, what if we take this surface integral here over that surface S of f of x, y, z, ds, and we let the integrand be 1. What is this going to give us? So I want you to, if you know it, excellent. I want you to think back to multiple integrals. What happened with a double integral when we let the integrand be 1? What happened with a triple integral when we let the integrand be 1? So with a double integral, if we let the integrand be 1, we found the area of the region. With a triple integral, if we let the integrand be 1, we found the volume of that solid region. So with the surface integral, if we let the integrand be 1 and integrate with respect to the surface area, we find the surface area of S. Woohoo! So we find the surface area of our surface. So that's something fun to keep in mind as you proceed with computation. So let's go ahead now and look at some examples.